Let us take up the next one, that is the next conversion of galvanometer into voltmeter. In order to convert the galvanometer into a voltmeter, you have to connect a very high resistance in series with a galvanometer. Suppose if you are connecting a very high resistance of R in series with a galvanometer, no doubt there will be a flow of current, that is Ig. Then in order to convert this galvanometer into voltmeter, what resistance must be connected in series with a galvanometer? That resistance is equal to V divided by Ig minus G, where G represents the galvanometer resistance, V is the voltmeter reading, Ig is the current for the full scale deflection in the galvanometer. Students, let us take up some few questions based on this moving charges and magnetism now. Let me read the first question for you. A beam of ions with velocity 2 into 10 power 5 meter per second enters normally into a uniform magnetic field of 4 into 10 power minus 2 Tesla. If the specific charge of the ion is 5 into 10 power 7 coulomb per kg, then the radius of the circular path described will be. Options are like this. Option A 0.10 meter, option B 0.16 meter, option C 0.20 meter and option D 0.25 meter. This problem is based on the force experienced by the charged particle in an uniform magnetic field. Whenever the particle moves in a circular path in the uniform magnetic field, its radius is given by the formula R is equal to mv divided by q into b. In this problem, they are talking regarding the concept of specific charge. Yes, the specific charge is nothing but the ratio of the charge of the particle to the mass of that particle. So, I can write the same equation like this, v divided by q by m into b, where q by m is nothing but the ratio of charge to the mass, which I can consider as the specific charge. So, velocity they are given 2 into 10 raised to 5, q by m is the specific charge, that is 5 into 10 raised to 7 into b represents the magnetic field, that is 4 into 10 power minus 2. So, 10 raised to 7 into 10 power minus 2, 10 power minus 5, that is going to cancel with numerator 10 power 5. Then it becomes 2 divided by 5 into 4, that is 2 by 20. So, that becomes 2 by 20, that is 1 by 10, that is 0.1 meter. So, the radius described by the particle in an uniform magnetic field is 0.1 meter. Therefore, the correct option is option A. Let us take up the next problem. If a proton, deuteron and alpha particle on being accelerated by the same potential difference enters perpendicular to the magnetic field, then the ratio of their kinetic energies is. Options: option A 1:2:2, option B 2:2:1, option C 1:2:1, option D 1:1:2. Whenever the charged particle is placed in the uniform magnetic field, when it is moving, it is going to acquire the kinetic energy. So, I can take that kinetic energy as I can take that kinetic energy as the work done. Work done is nothing but the charge into potential difference. Clearly in the problem they are telling that all the three particles, proton, deuteron and alpha particle, are accelerated through the same potential difference. So, if I maintain this potential difference as a constant, kinetic energy and the charge are directly proportional. So, kinetic energy is directly proportional to the charge. Then, if you want to find the kinetic energy ratio, then it should be equal to Q1 is to Q2 is to Q3, where Q1, Q2, Q3 are the charges of the particles proton, deuteron and alpha particle respectively. Proton 1H1, deuteron 1H2, alpha particle 2He4. So, what is the charge on the proton and the deuteron? Same. Then what is the charge on the alpha particle? 2 times the charge of the proton. So, this kinetic energy must be in the ratio 1:1:2. Therefore, option D is correct.
ಡಿಯರ್ ಫ್ರೆಂಡ್ಸ್, ನೀವು ದಿವಿಗೆ ಯೂಟ್ಯೂಬ್ ಚಾನಲ್ಗೆ ಸಬ್ಸ್ಕ್ರೈಬ್ ಮಾಡಿ, ನಿಮ್ಮ ಫ್ರೆಂಡ್ಸ್ಗೂ ಹೇಳಿ, ಇದೇ ಥರ ನೂರಾರು ವೀಡಿಯೋಸನ್ನು ಫ್ರೀಯಾಗಿ ನೋಡಿ.